Hello, everybody. Welcome back. Happy Wednesday. We got a full house in here today. 6 people already. Oh, down to 5. Yeah, so let me know who's here. Say hi in the chat. Suba says hello. Welcome to the stream. Wow, exciting chat today. Shutong, Patrick, good morning. James says, just brewed some Morning Joe. Excellent. Navik, hello. Taylor, good morning. Emma, good morning. It must have been my clickbait thumbnail that brought in the crowd today, it seems like. How's everybody's quarantine going? Getting through, I hope. Navik knows what's up. Make sure to smash that like button. That's exactly right. We'll get started in about a minute or so. All right, well, we could get started now since it's 9 o'clock. So we'll start like we start every class. With the simultaneous sip. So if you have your coffee ready or your water or whatever, please join. Yeah, so let me know in the chat you joined in on the simultaneous sip. And Supa makes a good point. Anyone not smashing the like button should be counted as absent. Well, I don't take attendance, so unfortunately, that's something we can't enforce. Taylor got the coffee emoji going today. That's nice. Okay, so yeah, we'll continue where we left off yesterday. We had this build-up, and we didn't get to the theorem. So let's state the orthogonal decomposition theorem, and then we'll look at a few examples. It's going to be a pretty example-heavy class today. So yeah, so I'm going to ask, when we're doing these examples, I'm going to ask for a little bit of feedback. It's okay if your feedback says, I need more time. We're ahead of schedule in terms of the semester at this point. So if you feel like we're going too fast, just try to slow me down. All right? So let's state a theorem, look at an example or two. So this is the orthogonal decomposition theorem, and it's going to generalize what we did last week with projecting a a vector onto a line, we're going to project a vector onto a higher dimensional subspace. So it could be a line, but it could be higher dimensional. So it says let W be a subspace of Rn. Then each y in Rn can be written uniquely in the form y equals y hat plus z. So this should look exactly the same as what we had before, except here we have W as a subspace, where previously we had L as just a line. Where y hat is in W and z is in W perp. Okay, so what this theorem says, and there's a little bit more to it, or like a second part to it, it says if we have a subspace in Rn and just some arbitrary vector, we can write it as a sum of two vectors where one of the vectors lives in W and the other one lives in W perpendicular. In fact, if U1 through UP if U1 through UP is an orthogonal basis for W, then the way we get y hat is just like how we got y hat in the case where W was a line. It's y dot U1 over U1 dotted with U1 times the vector U1 plus y dot UP over UP dotted UP times the vector UP. So this is how we get y hat, and the way we get z we take our vector we started with and we subtract y hat. Okay? So a little bit more notation before we could get to an example. This vector y hat we call the orthogonal projection of y onto W. And the way typically, I mean, you may see y hat, but typically you'll see this. The projection onto W of Y. Okay, and what this looks like, let's say this is the subspace W. And we have some vector, say this is Y, that's outside of W. We project it into the plane. And that gives us Y hat. And the vector that goes from Y hat up to Y, that would be Z. Okay, so this gives us a way to write any vector in high dimensional space as the sum of some vector that lives inside of a subspace plus a perpendicular component. Okay, let's take a look at an example. Write any questions you may have in the chat, and I'll answer them when I finish writing this example. Okay, so we'll let U1 be 2, 5, negative 1. U2 is equal to negative 2, 1, 1. And Y is equal to 1, 2, 3. Okay, so we'll let W be the span of the vectors U1 and U2. In your drawing, is Y hat and Z perpendicular? Yes. So let's draw that in. Yeah, Z is perpendicular. Z is perpendicular to any vector that lives in W. So in particular, it's perpendicular to Y hat. Okay, so we'll let W be the span of these vectors. So there's a few parts. First, we want to show that U1, U2 is an orthogonal basis. And then the second part is we want to write Y in this form as a sum of a vector from W and a vector from W perp. And then the last part, which we typically don't do, but I guess we should get in the habit of doing this because, I mean, it's just something it's good to be in the habit of doing. Let's check our answer. Okay, so there's three parts here. We want to first show that we have an orthogonal basis for W. We want to then write W as the sum of a vector sorry, we want to write y as the sum of a vector in W plus a vector in W perp, and then we're going to check our work. Okay, I know sometimes it's easy. You know, you work out a problem. It takes a few minutes, and you're just sick of the problem at the end, and you're just like, I'm done. I'm not going to check. Well, that's when mistakes happen. So yeah, we'll double check our answer at the end. Okay, so I'll give you, let's say I'll give you a minute or so to show this first part, then we'll all catch up. Then I'll give you another minute for the next part, catch up, and then another minute for the last one. Okay? So if somebody has a reason why U1 and U2 is an orthogonal basis, let us know in the chat. All right, so how can we show that U1, U2? Okay, yes, Taylor, exactly. Yeah, so we just basically, we know that it spans W, right? Why do we know that it spans W? Well, W is the span of the two vectors. So like by definition, it spans W. So what's left is just to show that they are orthogonal. So U1 dot U2 is equal to 2 times negative 2 plus 5 times 1 minus 1 times 1, which is negative 4 plus 5 minus 1 is 0. Okay, good. So therefore, we have an orthogonal basis for W. Right? It's a linearly independent set. Right? You can check that they're not scalar multiples of each other. Spans the whole space, so it's a basis, and it's orthogonal because they're perpendicular to each other. When you take their dot product, you get 0. Okay, and so now the next part is write y as the sum of a vector in W and a vector in W perpendicular. Okay, so I'll give you another minute and a half here. It may take longer for you to do this, but yeah, you could keep working on it while I work it out. And if you get an answer, maybe it's hard to type out what the vectors are, but what are the coefficients of U1 and U2 in y hat? All right, so we want to get y hat, and then we'll get z by just taking their difference. Y hat is equal to y dot u1 over u1 dot u1 times the vector u1 plus y dot u2 over u2 dot u2 times the vector u2. Nine thirtieths and 3/6 is what I got for the coefficients. Yeah, that seems right. Let's double check how we got there. So y hat, and again, we could have written the projection onto w of y. It's the same exact thing. Y hat's a little just cleaner to write. All right, y dot u1 is 2 plus 10 minus 3. That's 9. u1 dotted with itself is 4 plus 25 plus 1, which is 30. So yeah, Taylor, your first coefficient is right. And then the next one, we need y dot u2. So it's -2 plus 2 plus 3 as our numerator, which is 3. And our denominator is u2 dotted with itself, 4 plus 1 plus 1, which is 6. Okay, and so now we add these vectors together. Okay, and when we do this, I did it in my notes, but you can check the math if you don't believe me. You get -2/5 to 1/5. Okay, so that's y hat, and then to get z, that's y minus y hat. We get 7/5, 0, 14/5. So we could write y as -2/5 to 1/5 plus 7/5, 0, 14/5. Okay, now my question for you is, how do we check that these vectors are orthogonal? How do we check that y hat and z are orthogonal? Right, because if we ended up with vectors that are not orthogonal, then we obviously did something wrong. We'd have to try again. Yes. Yeah, Liza, exactly. So we'll take the dot product of y hat and z, and hopefully we end up with 0. -14/25 plus 0 plus +14/25. and it does equal 0. So, good. All right, I'll give you a minute or two. No, that's too long. I'll give you a few seconds to copy this down and ask any questions you may have. But if not, we can move on to the next theorem and look at some more examples. Again, this is going to be an example-heavy class today. I guess before we move on, I don't know if you all saw the email I sent yesterday. I'll get out of the answers there. I don't know if you all saw the email I sent yesterday, but I'm allowing you to make some partial corrections to your test 2. I said you could redo 2 of your questions for up to 5 points back. But I ask for you to submit that by tomorrow night. I forgot to put the spot to submit it on for the 9 o'clock class students, so that's available now. So just go, yeah. So if you make your corrections, you can upload it to Canvas before 11:59 Eastern tomorrow night, please. Okay. All right, so yeah, let's state another theorem. It's called the best approximation theorem. It says let W be a subspace in Rn. And let Y be any vector in Rn. All right, so same buildup as before. What the theorem says is then Y hat is the closest point in W to Y. That is to say, the magnitude of Y minus Y hat is less than the magnitude of Y minus V for all V in W that are not Y hat. Okay, so this projection onto the subspace is the closest point in the subspace to our vector. And we say that Y hat is the best approximation to Y by an element in W.
So this closeness to W, you know, the distance between y and y hat, how far away our vector is from W, that's going to be the main focus of section 6.5. Which will start tomorrow. We're skipping 6.4, unfortunately, but yeah. Yeah, so we're going to be interested in how far away a vector is from a subspace. That's going to be the type of question that we're going to try to answer. Okay, so let's take a look at an example. So we'll let U1, U2, Y, and W be all the same as the previous example. And the question is, find the closest point to Y in W, and how far away are these points? Okay, so we've already done a lot of we've done most of the work for this question. So the question is, can we, figure out, how do we find the closest point to Y and W? That's what the theorem tells us. And then how far apart are they? That's the next question. Okay, so I'll give you a minute to think about this. Feel free to type in the chat if you want to share how you would do this question. Yeah, the y hat we got in the last example is the closest point in W, right? That's what the best approximation theorem tells us. So I guess we already have the answer for y hat. And then how do we find the distance? Yeah, we want the length, but not the length of y hat. We want the length of y minus y hat, which we called z. So its distance is the length of z, which is the square root 49 25ths plus 0 plus 196 25ths. Which is the square root of 245. Twenty-fifths. All right, so let's take a look at another example with different vectors. So we'll let u1 equal 5, negative 2, 1. u2 equals 1, 2, negative 1. And y equals -1, -5, 10. So we'll let u1 equal 5, negative 2, 1. u2 is 1, 2, negative 1. Y is -1, -5, 10. And we'll let W be the span of U1 and U2. Find the distance from Y to W. Okay, now before you get started, here's the question. The question is, well, okay, I'm assuming this is what your thought process is. Tell me if I'm wrong. Your thought process is, let's find Y hat, let's find Y minus Y hat, and let's find its magnitude, and we're done. Right? Exactly how we did the last question. But in order for us to find Y hat using the technique with the dot products, Y dot U1 over U1 dot U1 times U1, Y dot U2 over U2 dot U2 times the vector U2. We need to first show, in order to do that, we have to show that we have an orthogonal basis, okay? So before you jump in and get started, that process won't work unless we have an orthogonal basis. So the first thing you should do is show we have an orthogonal basis, and then you can find Y hat and the distance, okay? I'll give you a few minutes. And again, ask any questions you may have in the chat. Okay, so we want to start, like I said, we want to start by first, we have to show that we have an orthogonal basis, because if we don't have a method for finding the projection at this point. Unfortunately, that's the techniques we learn in 6.4, which we won't get to. And so we have to show we have an orthogonal basis, so we could use the theorem that says this is how we project onto W. To show it's an orthogonal basis, you're right, Shutan. Let's just show the dot product of U1 and U2 is equal to 0. Five minus 4 minus 1 is 0. Okay, good. And now we could go through to find y hat. Right, y hat is equal to y dot u1 over u1 dot u1 times u1 plus y dot u2 over u2 dot u2 times u2. Y dot u1 is negative 5 plus 10 plus 10, which is 15 over u1 dotted with itself, 25 plus 4, 25 plus 4 plus 1. Y dotted with u2 is minus 1 minus 10 minus 10. That's negative 21 over u2 dotted with itself is 1 plus 4 plus 1 is 6. Which works out to be the vector minus 1 minus 8, 4. Okay, and just like the previous example, the way we find the distance from y to w is we want to find y minus y hat. Which is 0, 3, 6. And then we want to find its magnitude. Okay, but I guess something important to remember is we couldn't do any of this final process of finding y hat and all of that if we didn't have an orthogonal basis to start with. So on a question like this, you should confirm that we have an orthogonal basis before you get started. All right, let's write out one more theorem. So if U1 through UP is an orthonormal basis for W, okay, in the chat, what does it mean for a basis to be orthonormal? It's an orthogonal basis with one other property. Does anybody remember what that other property is? Well, while you're thinking about that, I'll write the punchline of this theorem. So if we have an orthonormal basis, then the way we get the projection onto W of Y it's Y dot U1 times U1 plus Y dot UP times UP. Yeah, exactly, Noah and Maddie. All of the vectors have unit length if we have an orthonormal basis. So what this theorem says is, well, let's write out our expansion as we did before, but if you have vectors of unit length, when you take the dot product with yourself, you're going to get 1. So all these denominators would be 1 in that case. So we won't have any of the denominator terms. A neater way to write this theorem is if U is equal to the matrix whose columns are the basis vectors, then you could find this vector. The way we project onto W is we do the multiplication U transpose times Y. Okay? So I'm going to write out an example. We're obviously not going to be able to finish it, but we could, we could either start it tomorrow, or if I have time tonight, maybe I'll make a YouTube video for it. Okay, so we have Y is the vector 4, 8, 1. U1 is the vector 2/3, 1/3, 2/3. And U2 is minus 2/3, 2/3, 1/3. And we'll let W equal the span. Okay, so there's two parts. So we'll let U be the matrix U1, U2. Compute U transpose U and U transpose. And you should answer this. What does the computation U transpose U tell us about this set of vectors? So that's part A. And then part B. compute the projection on the W of y and this product, U transpose y. And maybe explain why you're not surprised that you get the same vector both times. Okay. So yeah, either we'll start this tomorrow or I'll post a video onto YouTube explaining how to do that. But yeah, I'll send you an email at some point for information about the quiz. I haven't quite decided what it'll be on yet. Make sure you do those corrections, right? It's free money. Pick it up, 5 points. And as a thank you, as you thanking me, like button should be smashed before you get out of here. All right, so that's all I got. I have office hours at 11, but again, I'm doing literally nothing all the time. So just send me an email if you want to meet outside of office hours. Navik is right. And again, smash that like button. Yeah, okay. So I'll get out of the screen so you could write things down. But I'll hang around for a minute or so answering any last minute questions. But if not, I'll see you tomorrow. Emma says, thank you. You're welcome. See you tomorrow. James says, will do. Nope. Hard pass. All right. Well, it seems like there's no more questions. So I will see you tomorrow. Bye-bye.